Frequency Variable Electrosense. Northwestern Mechatronics Winter 2010. Our objective is to build upon existing research currently being done at Northwestern, utilizing electrosense technology, to see if information can be derived by varying the emitted frequency. We sought to send sinusoidal waves at discrete frequencies between 100 Hz and 10 kHz, read in the sensed wave using a PIC32's analog to digital converter, and then send these waves to a PC for plotting and analysis. By mounting the sensor on a one-dimensional linear actuator, we were able to gather additional information about objects and perform object detection and identification algorithms. The sensed wave is generated by reading in the two waves at the sensor electrodes and comparing their signals. This is done using an instrumentation amplifier, which multiplies the difference between the two signals by a fixed gain. If the waves are identical, then the output is nearly zero, with greater differences between the waves corresponding to larger amplitude changes. To read in the signal to the PIC, we must level shift the voltage so that it ranges from 0 to 3.3 volts, the acceptable range of the ADC. In order to generate the emitter waves at discrete frequencies from the PIC, we use an AD9833 function generating chip. We are able to send values from the PIC to this chip that correspond to the waves between 100 Hz and 10 kHz we require. Actuation is done using a linear drive screw driven by a stepper motor. This allows for very fine positioning control, with the downside that moving the sensor is fairly slow. The actuator is built into a 2-foot long by 6-inch wide tank for experimentation. The limits of actuation are determined using two mechanical switches. The control interface for the electrosensor is done using a GUI developed in processing. The window features plots of the emitted and sensed waves, and the corresponding FFT, phase, and magnitude plots. The data gathered at each frequency is stored and plotted in a Bode plot for each position of the sensor. An interface also includes buttons to control the sensor along with the various detection algorithms. The first step to setting up the system is to hit the calibrate button, upon which the sensor will home itself to position 0. Once calibrated, pressing the data acquisition button and then the activate button will begin the detection routine. The sensor will send out all the frequencies at position 0, feeding the information back to the user via the visual display. Here, the red wave corresponds to the emitted wave, while the blue wave corresponds to the sensed wave. Notice the changes as the frequency changes. The Bode plots are generated at each position as the user watches. After all frequencies have been scanned, the sensor will move forward a half an inch and repeat the process. Once each Bode plot is generated, it will compare the results to a library for different objects to see if the sensor is seeing an object at its current location. Additionally, it will attempt to make an object identification based upon the most similar library plot. While we have not had time to perform the number of tests required to correlate our results, preliminary testing shows some unique trends in the data that warrants further research. Different objects seem to have unique magnitude and phase plots. Additionally, it looks like position information relative to the sense electrodes can be derived from the Bode plots as well. Further research will be necessary to confirm these preliminary trends. This project was completed by Todd Reynolds, Josh Pang, and Pill Park.